first. Corin, do you have another question you said? Good morning, everybody. I know the people who just basically are watching probably know that we've been talking.
Yeah, I put it in the chat. I just asked if we have to reply to others for that chapter 1 discussion.
No. If you think there is a point you would want to pick up or you would want to, that's good actually. But you are not required to reply on this thing.
Okay.
The initial post is the one that is required. Okay. Okay. So again, welcome to chapter 2. Today we're going to discover Newton's law of motion, and that's a big day actually for any of you guys here, not because of the landing of Perseverance, which is really a big deal, and I'm hoping that you guys will join me and attend that thing. And it's because actually also the laws of Newton, the 3 laws of Newton that we'll be discovering right now, are probably the biggest deal in physics, or the most important laws that you're going to be discovering. And the promise is the following: if you know these 3 laws and you know how to apply them, technically there is no problem in physics that you cannot solve. Okay, so that's why it's an important day for you guys. So today is February 18th of the year 2021. So it's an important day for you guys because we're going to discuss these things. There are 3 laws for Newton. Law number 1 is basically the law of inertia. If an object is at rest, it wants to stay at rest. And if an object is in motion, it wants to stay in motion in the same direction with the same speed. So that's law number 1. Mr. Newton, when he formulated this law, he basically reworded the work of Mr. Galileo. So this one is basically the work of Mr. Galileo. The second law of Newton really states the following: if a net force is applied on an object. So the first law was you have an object and there are no net forces on it. So in this case, one object, 0 forces. So the first law applies. The second law says you have still one object and that object is actually under net forces. So what in the world is going to happen to it? It's not going to be the first law anymore. It's not going to be staying in its place. It's going to change motion. And the rate of changing motion, namely the acceleration, is proportional to that force. That is the second law. The third law, because so far the first and the second law dealt with only single object, and a single object either under no net forces for the first law, or under net forces in the case of the second law. So if the universe were made up of only a single object, then all you need is actually the first law or the second law. Is the universe made up of a single object? Do we have more than an object in the universe?
Yes.
Okay, I'm glad to hear that. So now the situation forces itself upon us, namely the fact that there is not a single object in the universe, we have more. So now we have to deal with that situation, and for that we invoke the third law. The third law says the following: so basically, we're going to tally the objects in the universe and see if they interact or they don't interact. If they don't interact, we can isolate them and treat them either with the first law or the second law, and we're back in business. If they do interact, we need to know how they do interact. If they do interact, and one of them exerts a force, and the second one will exert a force that is equal in magnitude to how much the first one exerted on it, and it's in opposite direction. So we have prescription of how to handle interacting objects when there is more than one. So when there is more than an object and they are not interacting, we're still falling back either to the first law or the second law. When they do interact, there is no way for us to treat that if we don't invoke the third law. So what this thing then does for us is it resolves everything in the universe. All these 3 laws, basically anything that we are faced with, theoretically, we can solve, okay? There are some technical issues because problems get a little bit more complicated and we have to probably use computers for that and things like this. But the point in here is that these 3 laws are all you need, okay? So let me share with you the PowerPoints, and I'm going to do a couple of demos today for you guys. So let me share. the screen in here. So what I have in here, and the trouble with this one is, where is my writing pen? There it is. The trouble with this one is, if I try to write, it's going to default to the first screen. It's not going to move to the second screen at all. So what I'm going to do is I'm going to move my Zoom thing back to the first screen and this one to the first screen. So if you guys, oops, let me stop sharing the screen first. I'm sorry about this, this technical thing in here, because I discovered that with another class, actually. I don't know if it was you guys or somebody else, that they cannot write on this screen. I can write on that screen, okay? So, so now I think I can do. Now I think I can write. Good. So that works. So basically, those are the 3 laws of Newton that we'll be discovering today, as I said before. So they are first law, which is really Mr. Galileo's work. Mr. Galileo was interested more in the dynamic of objects, how objects move. So he brought us the concept of kinematics. He brought us the concept of velocity. I mean, it's one thing to say one object is moving fast and another one is moving faster and a third one is moving even faster than the second one and a third one is moving, you know what? And the fourth one is moving what? You know, I can tell you, it's moving faster than the second one, but slower than the third one. Imagine you have 17,321 of this. Can you keep track of which one is faster, which one is slower? You can't unless you have numbers for it. So what he said in here is that this is actually the rate at which distance is changing with time. Okay. Now, if I can tell you, I'm doing 27 meters per second, and another object is doing 28 meters per second, and a third object is doing 37 meters per second, not only you know which one is faster, but also by how much. So numbers gives you more information that the simple language does not. So that's what Mr. Galileo did for us. He found an expression for the velocity. Instead of this language that can be very complicated and basically we cannot get anything out of it, numbers will do it. So that's basically what the D here stands for distance and this is time. So it's a rate. So the velocity is a rate of how much distance is changing with time. Then he came with another concept, Mr. Galileo.
I'm sorry, are we supposed to be seeing your screen? Because we see you.
Oh, I'm sorry. Thank you very much. Didn't I share the screen already? I thought I did.
Yeah, now we can see it. Thank you.
Please correct me when you see that, okay? So the velocity is the rate at which the distance is changing with time. So that's what Mr. Galileo did for us. Mr. Galileo also came up with the concept of acceleration. So acceleration is the rate at which the velocity is changing with time. So it's the rate of the rate. Okay. So those are the concepts that Mr. Galileo came up with, invented for us. And there is a way for measuring things. For example, if I want to know the velocity, I need to know the position now. So the position right now, and wait a second later on when the object has moved and find the position later. And this is the distance that I'm talking about. The time that has lapsed during this basically measurements is t. So just all I have to do is divide that by this, and I found how fast the object is moving. Let's say, for example, I take a car. A car, let's say, for example, was in this location, and after 1 hour, it has traveled 50 miles. Okay, so what's its speed now? What's the speed of this car?
Miles per hour.
50 miles per hour. Because in 1 hour, it does 50 miles, okay? If it does 50 miles in 2 hours, it's actually traveling 25 miles per hour because 50 divided by 2 is actually 25. So if t was not actually 1 hour, but took a whole 2 hours to do the same 50 miles, then obviously 50 divided by 2 is not 50, but rather 25 miles per hour. So that's the concept of speed, okay? The concept of acceleration is how much speed you're gaining per hour. You hear in the commercials, they tell you, okay, this car can go from 0 to 60 in, let's say, for example, 5 seconds. That means it's gaining from 0 speed, it's not moving at all, to 60 miles per hour in 5 seconds. So that means 60 divided by 5 is 12. So that means its acceleration is 12 miles per hour per second. Okay, so that's one way of looking at the acceleration, is that those commercials that they try to sell that these cars are sports cars and they can give super speeds. You can go from 0 to 60, 4 seconds, 3 seconds. So they are accelerating even more. Okay. So imagine how many G's you're going to be experiencing yourself. And that's exactly what the G is. It's this number. Okay. So the higher that value, the more G's you're going to be experiencing. So the first law of Newton is basically a rewording of Mr. Galileo's work, just in terms of the, of course, you guys, I know I'm writing on the screen and hopefully you guys are not confused with these things. You can write your own notes and you still have a clean version of this thing on your Canvas. So I just want to make sure that you guys have that. Anyway, the point being in here is that this the work of Mr. Galileo. He came up with the concept that an object at rest will stay at rest. Let me switch cameras quickly here. I have access to this thing quickly here. Let me remove that background first. And video, switch cameras. Yeah. See, I have an object in here at rest. Okay, you have this object in here is at rest. And right now there is no force exerted on it. So technically it's going to stay in its location. Okay, it's not going to be moving. So that's basically what the concept is. I also want to bring your attention to this coin in here. There is a quarter in here. I don't know if you guys can see it or not. That too is not in motion. Okay. So that object, if there is no net force on it, it's going to stay. In any object, there is no net force on it, it's going to stay. So that's basically the first law. The second law of motion basically states that if an object all of a sudden is under subject of force, its state of motion changes. Now it's gaining velocity, okay? And it probably left the screen, okay? So because there is a force, and the force is coming actually from the interaction between it and the paper. Okay? As I'm pulling on the paper, it's pushing on the paper and it's pushing on the support in here, and that is pushing back, and there is a friction between it. Imagine if there is no friction in here, obviously it's going to slide, the paper is going to slide, and the mass is going to stay in its place. So that's basically the second law. Second law says that an object will accelerate if in case it's under net forces in motion. No, we don't. The attendance, basically the way it works in here is through participation.
Okay, thank you.
Did you attend the first?
No, you sent me the code yesterday.
Okay, okay.
Yeah.
Also came in, I know there are a couple of people who joined us. Let me explain that the way the participation is taken in this class is by answering the items in the discussion. Hopefully you have watched the first video from the recording from Tuesday, so that you understand how the process works, because you're still responsible for that. So go back into the, there is a discussion specific for last Tuesday. Go through the entire video, you understand the process, how that works.
All right, thank you.
It's a good plan. Trying to do a thumbs up in here, but the camera is kind of, it's not the open camera, okay? Sorry about that, okay? So anyway, the point being in here is that this is the second law. The third law of Newton, again, I was talking about it, is the law of, in here it explains basically the concepts of forces and interactions. And the third law is basically the law of action reaction. And that's the one I was talking about, that between multiple objects, okay? And then we're gonna summarize Newton's laws of motion, okay? Okay, so here is the experiment we're going to do. As a matter of fact, this is the experiment. That demonstrates the law of inertia, okay? So I have an object in here. I'm gonna pull on it, Hopefully it's going to work, because sometimes demos don't work, okay? When you pull the paper fast in here, in this case, the object was at rest, okay? And it really resists the change in motion, okay? So you're trying to give it a tremendous acceleration, so it's going to have a higher resistance to the change in motion. That's, again, it works in this case, okay? Actually, as a matter of fact, if I pull it, and I did before, actually slowly, in this case, it's given time to build that change in motion, okay? So the acceleration in this case is small, so that the object can actually accelerate in this case, and the resistance in motion in this case is less. So basically, because you're applying less force in this case, F is less, and the acceleration is going to be proportional to this case to the force, okay? But if you do it this way, and I'm sure that you have seen this demoed with the cloth on YouTube and everywhere else, and by so-called. So basically, if you pull it fast, it's going to work. Very good. Same thing with this coin in here. If I pull it slowly, this was part of something I bought. I don't remember what it was, okay? Anyway, I couldn't find it. So again, it's going to slide out and the quarter will come out. But if I push it quickly, the quarter should fall. Oops, it did not, because I hit it on the bottom. Okay, it worked, okay? You see, and you thought physics doesn't work. Let me switch cameras again. Okay, video, change cameras. Okay. So that's basically the demonstration for the concept of inertia, which is really the first law of are we still on the same slide in there? Because going from cameras, hopefully I didn't lose that slide in there. Yes? You still guys showing the slide, Newton's first law of motion?
Yes, we can still see it.
Okay, very good. Because, okay. So a sheet of paper can quickly be withdrawn and the soft drink can without the can toppling because, okay, item 1 of the discussion, this is what I want you to do today, okay, is to try to do this at home. Pick whatever items that you have at home and try to demo it and post a picture of your demonstration of the first law of Newton, namely the law of inertia. Does everybody understand item 1? Yes.
So just do the same thing that you did in the demonstration.
You have a better experiment than this one, do it. Otherwise, this is a good idea to demonstrate the first law of Newton, the law of inertia. Okay. I want you to be at ease with it, that it works for you too. Yes. Andrea?
Yeah, sounds
Okay.
good.
Okay, very good. So hopefully everybody has picked up the first item of the discussion today. So the can has inertia. That's why basically in this case it's the can doesn't tip. So that's basically the idea behind it. Okay. If you swing at stone overhead in a circular, basically horizontal circle, and then the string breaks, the tendency of the stone is to follow a straight line, again, because of the same idea. This is the first law of Newton. Once the string is broken, because it was going to go in a circular path, but at any given point during its circular path, its tangent, its velocity is tangent to the path itself. So the minute it breaks, follows that velocity in the same line all the time. So basically, let me draw what this question is talking about in here, if I can find where my pen is. So basically, what you have in this case, you have it going this way. At any given point, the velocity is tangent. Obviously, there is a tether in here that's holding it, or in here when it was in here. So this is an earlier, and this is now. So if at this point this breaks, then this is going to continue in this path, okay? It's going to continue in this straight line. And again, who said that? It's the first law of Newton, the law of inertia, okay? Okay, this is the demonstrations. If you can do this one, that's actually great, but it did not work for me because I couldn't find a large enough mass to do that, okay? So this one also is another experiment that you can try. Do not try this one, okay? That's dangerous. Okay, so please don't do it, okay? Again, this is the same principle in here. And so when you flip a coin, yes, it's accelerating in this direction or it's moving in this direction, but it's not moving up and down, so it's going to stay in its path. And here's an interesting problem, that people challenge the idea that the Earth is actually moving around the sun. The Earth cannot be moving, they said, because how come this basically, if the bird tries to catch the worm and the Earth is spinning or moving around its axis around the sun, then the bird needs to be flying super fast in the forward direction to catch the bird, and we don't see that. So they're saying there is no way that this bird, yes, no, for chapter 2. It's still not available yet, so don't do it in chapter 1, okay? This is chapter 2. Corin. When the video is posted, you will have room in there where to post these things. Okay, so leave that discussion now alone. Don't mess with it. Chapter 1 is done. So we're in today. Okay, so here is what people criticize this idea of the law of inertia. They said that there is no way for the bird to catch the worm because if the Earth is moving, the minute it leaves, yes, right now it's attached to the bird, to the tree, but the minute it leaves trying to catch the worm and the Earth would have left it behind, and there is no way for it to catch it. Imagine basically how fast, let's say, for example, around the sun. The Earth is, the sun is here, and the Earth is in a big circle of radius. This distance is about 150 million kilometers. That is the distance from the Earth to the sun. So the circumference is 2 pi times the radius, 2 pi times 150 million kilometers. The Earth goes once around the sun in 365 days, that is in 1 year. So this distance travels in 365 days, and every day is 24 hours. So if I do the math in here, 2 pi is 3.14, 2 times 3.14 is 6 point something, times 150 million, it's going to give me a big number in here. It's going to be about 60 million kilometers or more, actually, more than 60. No, what is it? 2 pi, 2 times, that's 50, about 45 million kilometers. And divided by 365 times, it's roughly, it's going to be a little over 100,000 kilometers per hour. Okay, it's a big speed. Okay, if you do the math, I mean, should be not hard enough to punch it on a calculator and find what the answer is. Don't forget, when you divide, you're dividing by the product of these two numbers. You're not dividing by 365 by itself and then multiplying by 24. So this is in between parentheses. If you're going to do this on your calculator, you'll find 107,000 something. Okay, but the point being in here, the Earth is moving super fast. So how in the world a bird needs to catch the worm? It needs to be traveling super fast in order to move that fast. There is no car that we built that can travel that fast, or no bullet that we built that can travel this fast. Not even the fastest thing that man has made can travel that fast. I mean, the fastest thing that is right now, Voyager 1, basically, that is leaving the entire solar system, is not traveling with this speed. It's traveling with what, 40,000 kilometers per hour or something like that. So it's still not that fast. So the point being in here is there is no way for this bird to catch the worm. And the flaw in the argument, of course, is that when the bird is actually trying to reach the worm, it is already traveling with this much speed. So as far as the horizontal direction, it's going to keep that speed. Why? Because of the inertia. So all it needs, really, the bird, is to travel down, that's all. So it needs to gain velocity in the down motion, which really doesn't need to be that fast. It can move very small if it wants to. It can actually walk in here. If this one stays in its place, it can walk in here and still catch it, or fly super slow and gets to it. Because this one is traveling with that speed, this one is traveling with that speed, this one is traveling with, and the bird also, while it's flying down, it's still traveling with that speed in this direction. And why is that? It's because of the law of inertia. Everything is traveling in that direction. Now, if something stops the Earth today, we all will fly, just like that tether in the beginning. We all are going to leave Earth if we are not anchored to it. And we are anchored to it by the force of gravity, by our own weights. But if right now the Earth all of a sudden puts brakes on its motion and doesn't move anymore, then in this case we have a problem. We are all going to continue flying in the same direction, orbiting the sun, actually initially, but then we're going to travel in this direction, away from the sun, and the Earth will stop right in here, including the bird and probably the top of the tree and everything else will be yanked from it. And again, it's the law of inertia. Okay, so that was one of the criticism that was directed to Mr. Newton actually immediately. And actually Copernicus, when he suggested that the Earth was going around the sun, was this argument. How in the world you're going to argue that the Earth is moving at all? Because if it's moving according to your numbers, then this worm will never be this bird will never be able to catch the worm. And what they missed was the first law of Newton, because Newton came later, actually, came after Copernicus and after Galileo. Okay. The year, almost the same year when Newton was basically born, is the same year when Galileo passed away. So that's really there was an overlap, small overlap between the two. The second law of Newton is basically what I was saying in here. If an object were to accelerate at all, it must be subject to forces. Force, change direction, change motion, change acceleration. So actually, mathematically, we write this one, A is equal to F over M, or F equals to MA. This is a big law. It's a very important law. I know that you guys probably heard of MC squared and some other probably big laws in physics. This is one of the most famous ones that probably you need to know, okay? This is something you don't care for its applications, but force is equal to mass times acceleration. That is something that is a big deal, okay? So this law tells me that if I have a force, I have an acceleration. The mass in here plays the role of slowing down this thing. A heavier object or a more massive object will have less acceleration than a less massive object. Think about it this way. So you have a big object and all you can afford in the world is 10 Newton. Okay, and this object is 100 kilograms. Obviously, the acceleration of this one is going to be 10 over 100 according to this law, and it's going to be a mere 0.1 meter per second or per second squared. If I were, all I did was take 10 over 100, which is 0.1. If I only have 1 kilogram and I still have that 10 Newton, obviously this is less mass than this one, so it's going to resist less. As a matter of fact, the acceleration is 10 over 1, and 10 over 1 is 10 meter per second per second. This will accelerate a lot. Will suffer a huge acceleration, will change its velocity a lot faster than this one for the same force. So the role of the mass in here is the more of it, like in this case, the less the acceleration. The less of it, the more the acceleration. That's why we have it in the denominator in here, in this expression. Okay? That's why it shows up in the denominator. So this is a big deal. So in verbiage wise, we say the net force is equal to the mass times acceleration, but we write it usually in this form: acceleration is equal to net force over mass, because there is a cause and effect relationship in here. There is causality in here. This is the cause, and this is the effect. Okay, the cause in this case is the force, the net force. What results from that is an acceleration, and the acceleration is proportional to the force. obviously in here, there is something that messes up things for you, okay? And that is this guy, the mass, which is really which is the inertia of the object and its ability to change, to resist the change in motion, okay? So that's basically what that law is saying. All of this is really quantitative. I would like to end the class today around 10 o'clock. So we're going to leave a little early because of the event that we're having at 11 o'clock, because we'll be hosting that live basically broadcast. And we already so far saw an item for discussion. Hopefully you guys picked up on it already. Okay. So we're probably going to not finish everything today. So we're probably going to finish it by next week, Tuesday. So consider a cart pushed along a track with a certain force. If the force remains the same while the mass of the cart decreases to half the acceleration, okay, here is the thing. So the force stays the same. Let's say, for example, it's 10 newtons. And the mass, let's say, for example, was, let's take 10 kilograms. Obviously, 10 over 10 is 1 meter per second, okay? Or 1 meter per second squared. If they say in here, if the force remains the same, while the mass of the cart decreases to half. So this number is all of a sudden now 5 kilograms, and the force stays the same. It did not change. How much acceleration will I get now?
2 meters per second squared.
It's going to be 2. Did you say 2?
Yes, 2.
Okay, so it's going to be 10 divided by 5, which is 2, and you're absolutely right on that. So in this case, the acceleration will double. Okay, so if the mass is halved, the acceleration is doubled. If the mass is doubled, the acceleration is halved. Okay, because it's inversely proportional. Whereas if the force is doubled, the acceleration is doubled. If the force is halved, the acceleration is halved. Okay. Let's look at this one. Push a cart along a track so twice as much net force acts upon it. If the acceleration remains the same, what is reasonable explanation? Okay, so the acceleration stayed the same, and the force was a force before, and that was divided by a mass, and we multiply this force by 2. We doubled this one. This one stays the same. In order for this one to stay the same, this also must be doubled too. So if I have 10 newtons, for example, to go back into my original example, and I have 10 kilogram, obviously the acceleration in this case is 1 meter per second squared, because 10 over 10 is 1. But if I all of a sudden double the force now and make it 20 newtons, and I still need 1 meter per second squared, I really have to apply this one on 20 kilogram. The reason why I want that is because 20 over 20, I want it to stay 1. That is the condition in this case. They want the acceleration to remains the same. So if that's the case, so the only explanation is that the mass of the cart doubled when the force doubled. Let's look at the other options. The cart experiences a force that it didn't before. No, that's nonsense. The track is not leveled. Friction, no, the only explanation for this relationship is through doubling the mass. If you double the mass, you double the force, double cancel double, and now you're back to where you started from. Does this make sense to you guys?
Yeah.
Okay. Okay, when an acceleration is g, it is called the free fall. So when object, for example, you drop it, that's a free fall. Okay. This is a big, heavy object. Okay, so I don't want to drop it on anything because that is a free fall. Okay. The only trouble with this free fall is there is air surrounding it, so the acceleration is not technically exactly g. It's slightly different than g because of the air in the room. Okay. But if you do an experiment like this one in the lab, you're going to find the value of G immaculate, and it's going to be 9.8 meter per second, okay? Or 10, roughly about 10 meter per second. So when the only force acting on a falling object is gravity with negligible air resistance, the object is in a free fall. An object in free fall, when it accelerates toward the Earth by 10 meter per second. Sometimes you see me, and it's actually in all the books actually too, written as 10 meter per second squared. Instead of saying meter per second, it's the same thing, okay? So how much speed you gain for every second. So you write it that way. At one instant, an object in free fall has a speed of 40 meters per second. Its speed 1 second later. Remember, it gains 10 meters per second for every second. So that's what we saw. But right now, it's 40 meters per second and 1 second later. So how much speed is it going to be? Add to it another 10 seconds to this one. 10 meters per second to this one. So right now it's 40 meters per second. Oh man, did I jump that thing? I need to. So right now it's 40 meters per second. And each second we add another 10 meters per second. That's what the acceleration means. That means after 1 second, it's going to be 10 plus 40, it's going to be 50 meters per second. Okay? Yes, you're right. This is the same thing that we argued earlier. Okay, so if you double the mass, the acceleration stays the same because there will be twice as much force. Okay, because the acceleration is fixed everywhere on where you are right now. Okay, so if your value is 10.8 and this one is that mass, so I'm dropping the quarter and the heavy mass together, and the heavy mass is clearly heavier than the quarter, they arrive to my hand at the same time. We can do this experiment outside, and the campus where I went to school to, every year they go outside, take watermelons, take eggs, take all kinds of things and throw them from the highest floor to the ground. And there is an event, a day in the year to check Galileo's law to see if it still works, and they do that, and they have a lot of fun with it. And they check to see if it still holds. So it still holds too here. So I have a mass, two masses. One of them is clearly more massive. This is barely 5 grams. This is actually more than probably 100 grams. It's heavier than that. So and they fall to my other hand at the same time. That's what this experiment is saying. So G is the same. So the fact that I have more mass in this one, I have more force on it. So that the ratio of the force over mass is the same as the ratio over the force on this quarter versus the mass of this quarter. The mass of the quarter is 5.67 grams. Okay. Come on, oh, this one acts as a mouse sometimes. So a 5 kilogram iron and a 10 kilogram iron balls are dropped from rest. For negligible air resistance, the acceleration of the heavier ball will be the same. Acceleration is always the same when they are falling for the free fall. This is one of the things that Mr. actually Galileo himself went to the Tower of Pisa and demonstrated, okay? And people were watching, and obviously, if you take a feather and you try to drop it with a hammer, there will be a delay in the feather, and the only reason for that is because of the air resistance. But if you take similar kinds of objects with different masses, they will fall in the same time. So what matters in that case was the air resistance that is really changing the time when they reach the ground. So that was his argument there, and that was a beautiful demonstration. So that's what actually led to Mr. Newton to formulate that as being law number 1. Okay. So in this case, the acceleration is going to stay 10 meters per second. This is what I was talking about in here. Here is something that you have to be very, very careful with when you look at this analogy, okay? What he's saying in here, a heavier mass or a more massive object in here, big M, and subject to big F, so the ratio of F over M is always G. Here you have a feather, which has a little m, and has then it's a little f, so that the ratio is the same G. This G is supposed to be the same size. Letter-wise, the type itself. Whereas this type of F and this type of M are a lot smaller than this type of F and this type of M. The ratio is the same. Same thing, the analogy goes with the ratio of the circumference of a circle over that of the diameter. This is the same formula that I've used way back up there here, by the way, when I tried to find how fast the Earth is moving around the sun. 2 pi times the radius, or 2 times the radius is actually the diameter. So it's the diameter times pi. It gives you the circumference. So it's the same formula that I've used there. And this is a basic geometry formula that we use a lot. So the circumference is equal to pi times the diameter, or pi times twice the radius, because the radius is half the diameter, that's all. So this thing was discovered a long time ago, actually, by the, the Babylonians and people like that around those times, because people had so many children and they wanted to divide the inheritance, and they found some, usually which is land and farming lands and things like that. So they found this ratio between the circumference of a circle, it doesn't matter how big the circle is, and its diameter. And this number is a fixed number, okay? The Greeks appended to it the letter pi, the letter P from their language. And regardless of the size of the circumference and the diameter, the ratio stays the same. The trouble with this analogy is this is a mathematical true identity. It's true everywhere. So if tomorrow, for example, we contact beings from a different planet and another star, they know if they advanced at least fast enough in mathematics like we did, and they reach at least a level when the Babylonians reached it and then passed beyond that, they should have known about this ratio, that the ratio of the circumference of a circle versus that of its diameter is a fixed number, whatever they call it, they know it has to be 3.14, something like that. It's an irrational number, but that's something that they know. But the ratio of their weights over their masses is not necessarily 9.8. It's only 9.8 on Earth. As a matter of fact, it's different on the moon. It's different on Venus. It's different on Mars. So this is only true for us here on Earth. And as a matter of fact, even here on Earth, G is not the same everywhere. Near the equator is different than on the North Pole. And it's different when you go higher, for example, on the Himalayas, and when you go deep. So this is, G is actually not universal. So that's the thing that I want you to be aware of it. The point in here from this slide is the following. For the same location, the ratio of the weight over mass is a fixed number, regardless of how much mass it is. The more mass of object, the more heavier, the more weight it has. And that's basically the bottom line in here. So when acceleration is g, free fall, obviously when we do this experiment outside, it's not going to demonstrate that the two will arrive in the same time. We really have to do it in vacuum. If we do it in vacuum, this experiment will immaculately also produce the same result, in the sense that the two objects will reach the ground at the same time. Okay. Now, when you have air, it's a different story because you have the air resistance in here. And here is another problem that we experience. And today, one of the things that the Mars lander will be doing is is actually going to be, at some point, is going to deploy a parachute and landing in Mars. And because the atmosphere of Mars is a lot less than that of the atmosphere of the Earth in terms of its density and its pressure and so on and so forth, it really requires a bigger area for it to slow it down. And that's exactly what this thing is. So at some point, what the parachute will basically be thrown away, and then it's going to be sky crane basically into the ground. So that's really like you see it right now in the video. Okay. So the point being in here is that an object, if it has no air resistance, they will all fall with G. Now, when air resistance comes into play, this will slow them down, okay? This will slow them down. So an object will slow down. Actually, will be under not exactly its own weight, because weight minus the air resistance will be the new acceleration. So as the object is falling, it gains more and more basically velocity. And with more and more velocity, there is more and more air resistance. And this too starts to become of the same order of magnitude at some point will be equal, so that the object will not accelerate anymore, and it would have reached what is known as terminal velocity. So that's basically how this is working. So when acceleration is less than g, of course, it's not a free fall anymore. Free fall is when the acceleration is exactly g. Okay. Non-free fall occurs when two forces act on a falling object: the downward gravity and the air resistance. Case in point, when a 20 Newton falling object, 20 Newton falling object is about what? 2 kilograms. That's not a big object, okay? Because 20 divided by 10 is 2 kilograms. Encounters a 5 Newton air resistance, and its acceleration, of course, is less than g, because 20 minus 5 is going to be 15. 15 is divided by its mass. Remember, the mass in here was 2 kilogram, and a 5 Newton is 0.5 kilogram, so it's 2.5 kilograms. 15 divided by 2.5 is not equal to 10. Okay, it's less than 10, so it accelerates with less than 10. So if you're curious about the math, that's how it's going to work. So what you say in this case is the mass of the object is 20 Newton divided by g, and g is 10 meter per second per second. So obviously this object is 2 kilogram. Okay, the object, I'm sorry, 2 kilogram. And right now it's falling with 20 Newton, its weight, and 5 Newton up. So the net force on it down is only 15 Newton. 15 Newton divided by its mass, which is 2 kilograms, will result in an acceleration that is 15 divided by 2 is 7.5 meter per second squared. And 7.5 meter per second squared is not 10. This is not g. So this object is not in a free fall. Okay. I'm sorry, I made a mistake earlier by converting this one to kilogram. This is just a force. So it's less than g, because actually it's 7.5 meter per second squared. So when an acceleration is less than g, it's a non-free fall. As falling object gains speed, force exerted by the surrounding air increases, because they increase with velocity. Force of air resistance may continue to increase until it equates its weight. So here is an object that you drop from an airplane, for example. Initially, it's only its weight that is pulling it down. So it gains velocity. At some point, its weight will be started to be balanced by the air resistance. Now it's under less acceleration than g, and at some point these two forces will cancel exactly, in which case it's not going to accelerate anymore. It has reached its own last velocity that is going to be reaching, and that is the so-called terminal velocity. After that, it's not going to accelerate anymore. It's going to hit the ground with that velocity, okay? At this point, net forces are no further acceleration. Object has reached terminal velocity, continues falling at constant velocity with no acceleration, because these two forces cancel now. So there is no net forces, so we're back to the first law of Newton. How are we doing? Still have about 10 minutes. Any questions so far? Let's look at this question here. Please don't try this one at home. You have a 50 Newton person is to fall at terminal speed. The air resistance is, so that person reached terminal speed. Let's find the mass of this person. The mass of this person is its own weight, which is 50 Newton, divided by g, which is 10 Newton, and 50 divided by 10 is 5 kilograms. 5 kilograms is 11-pound person. What is that person? Does anybody know?
A child.
A baby, actually. 11-pound baby. That's still probably not too long ago since that one is born. Don't try this at home, okay? If you do, you're gonna be it's criminal.
In jail.
Sorry, don't. Okay, so sometimes the text in here, the people who put it, they don't think about these things, okay? 500 Newton person, it's still 50 kilograms, it's a child, okay? 50 kilograms, probably a teenager, okay? 70 kilograms, 80 kilograms, now you're talking about 170 pounds, 180 pounds. That's a grown-up. Okay, that one you can put a parachute on him or her and drop them, and if they're trained enough, they will deploy the parachute on time so that they can reach their terminal velocity. Okay, so they should be able to do that. But a 50-pound person, 50 Newton person, that's 5 kilograms. That's 11 pounds. That's scary. Okay. Is to fall at terminal speed, the air resistance needed is, of course, has to be exactly whatever the weight of the person is. Okay. G is constant. Okay, this is an answer to Gretel, that G is the acceleration on the Earth. G is always. Did I say 10 in here, Newton? I'm sorry, it's supposed to be 10 meters per second squared. G is a fixed number, 10 meters per second squared. That is fixed on Earth. It's roughly that number. It's 9.8 to be more specific, okay? That is an acceleration. That is not a force. The force in this case is, like, for example, the weight of the person. Like in this case, 50 Newton. That is weight. If that person is in free fall, that person has an acceleration that is equal to G, okay? But if the person has reached a terminal velocity, okay? So in this case, the air resistance must be also 50 Newton. So this is your air resistance, okay? Cancel these two forces, the net forces are equal to 0, then the acceleration in this situation is 0. Because 50 minus 50 is 0 divided by the mass of this person, which is 5 kilograms. 0 divided by 50 is going to be 0. So it's not G anymore. It's less than G. As a matter of fact, it's exactly 0. We are in terminal velocity now when the acceleration is 0. Does this make sense to you? Okay, very good. So that's basically how this thing is. So the air resistance is variable. It changes. Initially, when the person jumps off of the plane, there is no air resistance at that point. As he or she gains speed, the air resistance builds up until it reaches the weight of the person. At that point, there is no more air resistance that can pile up on top of what's already there. No, Corin. The answer is no. Not this type of math that is required, but it helps us to understand what's going on. Does this make sense to you, Colin? Okay, very good. It really, the numbers tell the story a lot better than trying to explain it with words, okay? That's why these numbers in here illustrate the points. That, okay, as the person jumps off the plane, at that point, there is no air resistance. It's only the weight of the person at play. The weight of the person would drag him down because F equals to ma, and A in this case is exactly G. But then air resistance starts to build up because the person is gaining speed. And as it starts to build up, the acceleration now is less and less than G because it's the weight minus the new air resistance divided by the mass of the person. That doesn't change. The person does not all of a sudden gain mass or lose mass unless on the way he decides to cut his hand or something, then that's another story, okay? That person has something else in his head that hopefully, I don't know what it is, okay? So the person does not gain mass, does not lose mass, so the denominator is the same, the numerator is changing. And it's less and less until it reaches 0, when the person has built up enough air resistance to balance the weight that is dragging down. At that point, the two cancel, and there is no more acceleration. We say we have reached terminal velocity, okay? I know we still have about 5 minutes. That's the time as I promised. Let me give a point in here because it's going to illustrate the discussion that we will have all the way to slide. Because all of this is just, this type of force, this type of behavior is called the drag force, okay? This force actually that we're talking about in here is called the drag force. This one. Which is actually air resistance. The drag force is an air resistance. So in order to have a big enough drag force, because you would want to have a less terminal velocity as you jump off a plane, you would want to reach this terminal velocity as soon as possible. You would want to have a surface that is big. That's why you build a parachute. The bigger the surface, the more air resistance you're going to have, the more drag force you're going to build. That's number one. It also depends on the temperature, but it's slightly, okay? It depends on the density of the air. For example, the density of the air on Earth is about 1.29 kilograms per cubic meter. On Mars, it's hundreds of that. It's very small. So the density now becomes a problem. So if we want to drop something on Mars, we really have to build even bigger parachute, or make the load less, or make the object weight less, okay? If the weight is less, then we will reach that terminal velocity faster. In other words, if I have two people jumping over the same plane, one of them is supermassive person with, let's say, for example, 100 kilogram, that person is clearly overweight, versus a person who is, for example, underweight, let's say, for example, 60 kilograms or less, 50 kilograms. Obviously, the 50 kilogram will reach terminal velocity quicker because his or her weight is 60 times 10, which is 600 Newton, and all they require is 600 Newton. So all they need to accelerate is a little, and now they have built their terminal velocity, and now they're on free fall, okay? Whereas the person who is 100 kilogram, his weight now is 100 times 10, which is 1,000 Newtons, would need to wait to build more velocity to wait to reach, for another 1,000 Newtons from the air resistance to cancel his weight or her weight. At that point, they would reach also the terminal velocity. But the terminal velocity of the heavier object will be higher because it needed more time to reach the terminal velocity than the lighter object. So the heavier object will hit the ground with a higher velocity than the lighter object, okay? So that's really something that you need to take into account. So that's what really people are doing in NASA, trying to understand that. And that's actually part of the challenge that I have for the STEM students. And if you guys are interested, you're welcome to attend. And it's part of the flyer that you received yesterday by March 11th, that you're supposed to simulate a landing on Mars by building your own parachute and basically making sure that your rover lands safely on Mars. Of course, you're going to do a simulation at home, make a video and post it on there. And then we'll have a discussion on March 12th, which is on Friday, the day after. So do you guys understand the terminal velocity and how these things work? At least a little bit conceptually?
Yeah, somewhat.
Okay, very good. So if you want to, you are very welcome to attend, to participate in the Mars rover basically challenge that we have for March 11th. And it's open for everybody. So the fact that probably you're not a STEM student doesn't matter, okay? So join me, okay? I like these things, okay? Hopefully you like it too. You're gonna do it with eggs, so don't worry about breaking anything. Okay, so, okay. Let me get into another point in here that I want to. Yeah, this is the same thing. Actually, I can give you the formula, but probably it's not gonna help much. Okay. So this is exactly the same point I was talking about in here. Who will reach? So basically what you have, consider a heavy and light person with same size parachutes jumping together from the same altitude. So who will reach the ground first? Obviously, it's going to be the heavier person. The reason why is because that person needs more basically time to build up the terminal velocity, and that terminal velocity will be higher than the terminal velocity of a lighter object, okay? So that's really the key point in here, because the weight is higher. So here is the weight, for example. This one is 1,000 Newtons, and the first one is 600 Newtons. Obviously, this one will need just to build enough air resistance to compensate for the 600 Newton, and now he or she is cruising at their terminal velocity, whereas this one will really wait a little later to build up more air resistance to compensate for his or her 1,000 Newtons to fall, okay? So now this one will have to build more velocity to reach that terminal velocity, to reach that air resistance that compensates for the weight in here. And now this one will be probably falling with a lot more speed. So this is V terminal is bigger than this V terminal, and this one will hit the ground first because now it's moving faster. That's why it reaches the ground first. So the person who is heavy will reach the ground first, and with a more velocity than the lighter object that hits the ground later with less velocity. Okay, here is the item 2 of the discussion for the day. I want you to watch the live recording today on the Mars landing, or if you cannot make it, because you probably are not scheduled to have a class during that time, watch it later, okay? And please put it in your own words. What do you think we hope to achieve from this mission? Okay, there are several components to it, by the way. There is the study for the, and we can talk about it later on, for the astrobiology in terms of determining whether or not there was biological, basically living organisms on the planet itself. And if they did not, why they did not, because the conditions were suitable for it. Because we're landing on Jezero crater, which is a place where we're supposed to have had water in liquid form, which is suitable for life, at least on Earth. And Mars was a water world, meaning that the climate was suitable for that. So that's probably one of the things. The other thing that we'll be doing is we'll try to see, try new technology in terms of see if we can build a drone that can hover over the planet because of the low density. That is going to be very hard to build enough drag force again for the what do you call it? Not the airplane, helicopter, basically, to lift off from the ground, which is something that we're trying to do. If in case we go back, we need to come back from the planet. So we really need to learn how to fly in that environment. So the other thing also is that we're trying to make oxygen out of the atmosphere for our manned missions in the future, and also to for fuel for the return trip, because we need to burn methane and other hydrocarbons in order to fly back. So that's one of the things. We also are capturing soil samples in there, and we're putting them in sealed containers so that by the year 2026, we want to go back, or at least sometime in the future around that time, to go back and collect those samples and study the rocks here on Earth. There are a lot of things in there. There are a lot of cameras that we're testing them also, and we're testing the terrain and things like that. Again, you don't need to participate in the building. There was a question about the building or rover. There is actually another project altogether that I was involved with, supposedly with the STEM students, but because of COVID, we could not do it. And that is to actually build a model of the rover, okay? What we're doing right now is just simulating the landing on Mars as part of the project, and you're welcome to participate in that. That is not part of today's item 2 discussion. Item 2 discussion, again, is to simply tell me, what do you think, in your own words, we will be achieving from this mission? Okay? If you cannot watch it live, you can go, yes, it's going to be on chapter 2, and you can post it in the discussion in there. Hopefully you attend us live. If not, you can watch it later on and see how the landing happened and things like that. But it has to be after the landing is successful. Remember, the landings are 50-50 so far. We really don't have a good record in terms of landing. So that's why we're hoping and praying that everything will go as scheduled. Okay. The stream, actually, Danielle, you should have received a message from me. And I think also the STEM Center sent a message directly to everybody. It should be in the flyer that you guys have had yesterday. That I sent it attached to the message I sent yesterday. Did you receive it, Danielle? Oh, yeah, you put it in discussion for chapter 2, yes. Because down the road, we will be doing astronomy. I mean, it's unfortunate, and I complained about that last time, that the landing is happening toward the beginning of the semester, not toward the end, but that's something that's out of our control, okay? Oh, you can rewatch it actually on YouTube, okay? Probably we will see how NASA will send the link, and I will probably post the link again. Okay? Does this make sense to everybody? So we have 2 items today, and you guys know what they are. So if you're watching this recorded afterwards, hopefully you're going to be live with us. If not, you will have a chance also to keep up with these things. Like I said, I really have to get ready for that meeting today at 11 o'clock to start. So I'll see you guys then. If not, I'll see you Tuesday of next week.
I have a quick question about the textbook.
Yes.
Does it matter if it's a hard copy or if it's an ebook?
The ebook is fine.
Okay, all right, thank you. Sorry.
Ebook is fine. Okay.
For the
Anybody else?
first item, do you just want a picture or a video of the experiment?
Either. Okay.
So, okay.
Picture will do.
So we just set up the experiment, or what do you want for like the pictures?
Whatever capture the essence of it.
Okay.
Okay. You'll be the judge. You are the scientist. You tell me. Okay. Okay, very good. I see you guys on hopefully 11 o'clock. If not, I'll see you guys sometime in next week, okay, on Tuesday.
Hey, Professor,
Thank you guys.
Professor.
Bye. Okay, did I do a recording or not? Yes, it's recording. Let me stop the recording first.